Thank you, Robert, and welcome to the webinar. As Robert said, my name is Joe Celia. I'm the Technical Manager at AIS, and I'm one of the team who worked on the new acoustic guide to offices. My background is in the fit-out industry, in particular partitioning, where I've worked since 1979. So, today we are going to run through some basic acoustics. We're going to talk about noise in offices, and I'm going to run you through the design guide to Office Acoustics, and we'll finish off looking at some of the new materials that are coming into the market. Firstly, though, a little bit about the AIS. AIS represents the interests of quality companies involved in the manufacture, supply and installation of all aspects of interior fit-out and refurbishment. With some 1,100 offices nationwide, a combined workforce of over 38,000. Members carry out over 65% of the work involved in the UK commercial interior fit-out, refurbishment and retrofit sector, which is worth over £4.3 billion. The Association of Interior Specialists' vision is to be the pre-eminent interiors association, recognised in its business for the quality and excellence of its membership. And part of that is the vetting process that we have, where all members go through on an ongoing basis. AIS also offers information to specifiers and architects in the form of site guides, and all of these site guides are available from our website, and they're available for you to download at no charge. We also look at innovation and work done by our contractors in a number of awards, and that again is done on an annual basis. And if you follow the website, you'll see some of the work which is done, including an example here of a vertical rising folding wall. So, on to the seminar itself. And the key learning points that we're going to go through today is to help you understand the physical properties of sound, how it's measured, how it travels, understand how sound can be controlled, either through absorption, insulation or diffusion. Understand how products are tested in a laboratory. Understand the different descriptors that are used. And understanding about flanking sound and how that can really affect the sound performance of a partition. Understand the effect of exposed soffits will have on the acoustic performance of a space. We're going to look at being able to plan by zoning spaces depending on the activity and background noise levels. We're going to help you select partitions to meet the requirements based on background noise levels and privacy requirements. And then we're going to, as I say, run through some of the finishes that are available and the sort of effect that those may have on reverberation in the space. So, a couple of things about basic acoustics. Good acoustics, they're essential to productivity. And one of the little-known facts is that about 85% of a building's cost is the cost of the staff who work there. And if they're unproductive because the space itself won't perform in the way that they need to, their productivity will fall. So it's a very small proportion of a cost's overall building is actually the building itself. But understanding acoustics is certainly not new. The Greeks have understood this for a long, long time. In fact, the word acoustics comes from alken, which means to hear. And when they started building the churches in England, I'd seen various things above pulpits, and I must admit, I thought at the time they were there to stop, bats and things dropping things on the preachers. But they're actually sounding boards, so the sound would reflect from the pulpit, and so the whole of the audience could actually hear what's going on. But I'm going to try and explain now actually what sound is and how it performs. And the best way for me to do that is to think of it in terms of water. If you imagine a very still pool and you were to drop a pebble into the center of it, you would see these ripples radiating out from the source in much the same way as sound actually radiates out from a source. And if those ripples hit the side of a pool, they'll bounce back in. They'll reflect back in. And likewise, the sound itself, the further you get from its source, as with waves, the energy dissipates. And so the further you are from the source, the quieter it appears to be, because the energy in it is now being absorbed. And if you get too much energy bouncing around on your pool, then it becomes really quite noisy. And in the same way as that still pool now has become quite a mess, it'd be very hard to see or hear an individual within all of that. But sound itself is energy passing through a medium. It doesn't actually mean that the molecules within that medium move. So the old cartoons of somebody shouting and the hair of the person listening getting blown back actually doesn't happen. The best way to describe how the energy is transmitted through the space is using a Newton's cradle. Now what happens with a Newton's cradle is that the energy is put in at one end, passes from ball to ball, and the energy then is transferred out to the other side. And that's exactly what happens with sound. So the energy itself doesn't move the molecules, but it's the energy from molecule to molecule that actually moves. I'm going to go back just one slide because I want to show you how we measure sound. And back to our ripples, the length between one ripple to another, or one wavelength to another, is measured. The amplitude, how much energy there is in the wave itself, is also measured. And then the frequency, how often those waves go past you, is also measured. So they're terms that you're probably quite familiar with. When we measure sound, and we're measuring the pressure level in the sound, we use a table of decibels. And decibels were named after Alexander Graham Bell, and they're simply a method of measuring one thing against another. It's not a linear scale, it's actually a logarithmic scale. So that is to say, we would understand a difference of 10 decibels as a doubling of sound. So conversely, if we were to reduce sound by 10 decibels, we'd perceive that as a halving of sound. So to go from 20 dB, we'd perceive that as a quarter of the original sound coming through. 30 dB would be about an eighth, and 40 dB about a 16th of the original sound coming through. When you start to get above that, you can imagine to go from 40 to 50 dB, you're talking about doubling the performance. And it's a bit like getting a racing car to go from 100 miles an hour to 200 miles an hour. It's very, very hard at that level to increase the performance of a partitioning, certainly as you get above those sort of rates. And one of the things to try, if you ever get a chance to get hold of some ear defenders, and you'll see them in B&Q and places like that, put them on and walk around and just listen to what's going on. That's a reduction. They're generally rated at about 25 dBA, depending on the frequency, but broadly about 25 decibels. And normally with a partition you can be looking at around about 40 decibels, 35 to 40 decibels on site. So what happens to our sound from the source? So as we explained using the water, it reflects, and actually it reflects in a very similar way to light does. So if it hits a hard surface, it will reflect around a room. And that's what comes back to us. And if you're in a room with too much absorption, you might feel it as being a little bit dead. You can't quite hear where the sound is coming from. Too much reflection and you get this not quite echoey sound, because an echo needs the back end of one word to stop before you hear it coming back again. Quite a gap between the two. But just a reverberant room. And that reverberation is something which is used by acousticians to measure the performance of a room and how a room can meet the requirements of the users itself. And we control absorption by, we control reverberation by using absorption. And I'm going to try an experiment here. I know we're all online, but if you ever see me do this, you'll see me picking up ping pong balls and throwing them around. You should be able to hear this. So I've got a ping pong ball bouncing around on my desk there. And of course, if you get too many ping pong balls bouncing around, the room gets very noisy. Now I've got a little reverberation chamber that I've created in this room that I'm at now. Oh, can you hear that? I hope that it's really quite reverberant. If I put something soft into that reverberant room, you should be able to hear there's a difference between there, and that's because the energy that I'm transmitting has been absorbed by the soft materials. So generally it's quite a soft material which provides absorption, and as absorption is good for the people within the room. Makes the quality of the room much better than can be the case. So if you're an acoustician, you want to know how absorbent a product is so that you can design it accordingly. Well, this is a reverberant room. It's a controlled room within a laboratory, and you can see very hard surfaces, concrete there, and those pieces hanging from the space are diffusers, and the diffusers are there to make sure that there is an even spread of sound throughout the room. So they'll put some sound in the room, generate it, it'll bounce around, and they'll work out how long that sound takes to diffuse, to dissipate down from its sound source by 60 dB. Then they put a sample in the room, and in the case of a ceiling, it can go on the floor. Doesn't matter where it is within the room, but normally with the sort of air gap that you would get behind a suspended ceiling. And they do the same test again, and they measure the difference, and the difference is measured in seconds, or really fractions of a second. It's then possible to classify those products by their absorption based on the frequency of the sound as well. So if you look at this here, you'll see that the frequency down here will affect the absorption of the product. And so they're classed A, B, C, D, and E. And that's done to a standard. It's a British standard, EN ISO 11654. Fairly typical way, and you'll see this particularly on a lot of ceiling products, because ceilings really offer the largest area of absorption within a space.